Every time you see a skyscraper just scraping the clouds or a massive bridge stretching across a river, you're really looking at the result of some seriously incredible precision. This isn't just about big blueprints. We're talking about getting things right down to the millimeter. And it's all made possible by high-precision GNSS. So that's what we're going to dig into, how surveyors pull off this kind of pinpoint accuracy.
So, here's a question for you. Why can't you just use your phone's GPS to build a bridge? I mean, it's a modern marvel, right? It gets you to that new coffee shop, no problem. But, and this is a big but, if you actually tried to build a bridge with it, well, you'd be in a world of trouble. And understanding why is the key to understanding the entire world of professional surveying.
See, for a surveyor, everything, and I mean everything, boils down to this one big quest: getting the exact level of precision a project needs. This is not a one-size-fits-all kind of job. It's all about picking the perfect tool, the perfect method for that specific job every single time.
And here's the real difference in a nutshell. Your phone is designed to get you within, say, a few meters of your target. That's awesome for finding a doorway, but it's a catastrophic margin of error in construction. Professional GNSS, that's Global Navigation Satellite System, is playing a completely different game. It's aiming for centimeter, and often even millimeter accuracy.
Okay, so this brings us to the very first, most basic decision a surveyor has to make. Think of it like the first big fork in the road, and it pretty much determines the whole approach for the project. Is your gear going to be sitting perfectly still, or is it going to be on the move?
That single choice leads to two totally different philosophies. Let's use a photography analogy. On one hand, you've got static surveying. This is the tripod approach. The receiver is locked down, it's patient, and its one and only goal is to get the highest accuracy possible, kind of like a long exposure photo. On the other hand, you've got kinematic surveying. That's your Steadicam approach. The receiver is always in motion. The goal here is all about productivity, covering a ton of ground as fast as you can.
All right, let's head down that first path, the static branch of our decision tree. This is the route surveyors take when accuracy is everything, and they've got the time to make sure it's absolutely perfect.
So what does static surveying actually look like? Well, it means you're setting up at least two receivers. One is called the base, and it sits on a point where you already know the exact coordinates. The other one, the rover, gets placed on the new spot you need to measure. And then, they just sit there, patiently listening to the same satellites for a good long while. Could be 30 minutes, could be several hours.
The whole process is very methodical, very deliberate. You set up your base, you set up your rover, and you wait. You just let the equipment soak up a massive amount of data. All that observation time lets the system average out all the tiny errors and calculate an incredibly precise position. Once that point is done, you pick up the rover, move to the next spot, and do it all over again.
Now, even on this patient path, you've got options. Classic static, where you might be observing for hours, that's the gold standard. It's for establishing those big, super accurate control networks. But if you need to move a bit faster, there's something called rapid static. Here, you're only observing for maybe 2 to 10 minutes. It's perfect for adding more reference points to a network you already have. And the best part? You can actually turn the receiver off between points. That's a huge time saver.
But what if you have to survey, like, hundreds of points or map an entire highway? You just don't have time for a tripod. You need a Steadicam. And this is where we jump over to the world of kinematic surveying. Here, the name of the game is motion and getting the job done fast.
With the kinematic method, your rover is almost always on the move. You might see it on a surveyor's backpack, mounted on a truck, or on a pole that's moving from point to point. It's built for jobs that create a huge volume of data, like making a topographic map or staking out hundreds of building corners on a construction site.
Of course, all that speed comes with a price, and it's a big one. To get accurate results while you're moving, that rover has to maintain a constant, unbroken lock on at least 4 satellites. If you lose that lock, maybe you walk under a bridge or through some dense trees, the whole system has to reinitialize. And trust me, that's a process that can just kill your productivity for the day.
So, to wrap it up, kinematic is, without a doubt, the most productive method out there. It gets you incredible centimeter-level accuracy, which is just what you need for most construction and mapping work. That need to maintain satellite lock? Yeah, that's its Achilles heel. But it's a trade-off you make for speed. There's even a variation called stop and go, where you pause for just a couple of seconds at each point to boost the accuracy.
So we know kinematic surveying gives us that incredible speed,
But how we actually deal with the data from the field, well, that leads us to one final, really important decision for any surveyor on the move.
And the question is this: do you need to know your exact coordinates the very second you measure them? Or can you just gather all your data out in the field and figure out the precise locations later, back in the warmth of the office? It's kind of like using a digital camera and seeing the photo instantly versus the old days of having to take your film to get developed.
This choice gives us two final methods. First, on the left, you've got RTK, or real-time kinematic. This is your instant photo. A radio is constantly beaming correction data from the base to your rover, giving you centimeter-accurate results, live, right there in the field. The catch? You're tied to the range of that radio, which is usually less than about 10 kilometers. Then you have PPK, or post-process kinematic. This is the develop later approach. You just collect your data, no radio needed, and process it all back at the office. No radio means no range limits, which gives you way more flexibility.
And the power of post-processing is just amazing. You take your raw data and combine it with data from a base station using some pretty powerful software. But get this, you don't even need your own base station anymore. You can use data from public networks of these permanently running reference stations. There are even free government-run online services where you just upload your raw data file, and a little while later, they email you back your perfectly calculated, precise coordinates. How cool is that?
Okay, let's bring this all home. We've basically just walked through a surveyor's decision tree. We started with a simple question: are we staying still or are we moving? And it led us all the way to this full suite of incredible high-tech methods. This right here is the modern surveyor's toolkit.
At the end of the day, it's never about one of these methods being better than another. It's all about the trade-offs. You're in a constant balancing act between the need for speed, the demand for accuracy, and the unique, real-world constraints of whatever project you're working on.
And when you choose the right tool for the job, the results are just staggering. With a technique like rapid static, a surveyor can nail down a point's location to within about 5 millimeters. For perspective, that's about the thickness of a couple of credit cards stacked together. I mean, that is just a mind-bending level of precision.
Which kind of leaves us with one final thought. All of this incredible power, which used to require super expensive, specialized gear, is getting smaller, cheaper, and easier to use every single year. So as this millimeter-level accuracy starts to find its way into our everyday devices, it just makes you wonder, right? What are we going to measure next? What new things will we be able to build?